Okay, so let's go to 26.5 parallel plate capacitor. And the reason why we are doing this parallel plate capacitor right after the electric field of the disk is because we can use this for various things. We've been working so far, we worked with a ring, we've worked with a point charge, and if you look at the electric field of a point charge, you can see that it goes out radially from the point. It's not a constant, it falls off as 1 over r squared. If you look at the electric field of a line, that also is radial. So the parallel plate capacitor is a way to create a uniform electric field at some point in space. Okay, so that's the advantage of having a parallel plate capacitor. You can put two charge plates together, you have a uniform electric field. There is no other way to create a uniform electric field in space except with a parallel plate capacitor. So let's look at that and understand what's going on. So we shall say a parallel plate capacitor is useful for producing a uniform electric field in a space. It is made up of two charged plates parallel to each other. So if we say the two plates are parallel to each other, then we shall have, for example, let's say we have a plate like that. So we have one plate and a second plate, and I've exaggerated it. Typically, you want the plates to be very close to each other, but I have to draw them farther apart just to be able to label them. So the distance between the plates can be d, and on this plate we can have positive charges, and then this will be negative. So that will mean that this is basically set up like that. So if you think of it that way, I'll just take the plates out now and leave out, I'll just put this is positive and that is negative. That means that I have an electric field that way going from one to the other. You can see the field is very uniform. That's the whole idea. So if the plates are very large and close to each other, then you have a very uniform field between them. So if this is negative, so the negative field outside goes this way to the negative plates, and the positive goes that way. So in between the electric field, we're going to have a positive that goes that way, and a negative component that goes that way. So this tells us that we can quantify the electric field. So this is E. We can quantify the electric field between the plates by knowing that, or by knowing the field of an infinitely charged plate. So we're going to use a field of an infinitely charged plane, or infinite charged plate. We know that field is given by eta over 2 epsilon naught. So we can say that in between the plates of the capacitor, we have the magnitude of the positive plate plus the magnitude of the negative plate. This will give us the E between the plates to be E for the positive plate plus the E magnitude for the negative plate. We are interested in the magnitude because both of the fields are pointing in the same direction in between the plates. The negative electric field goes towards the negative plate, and the positive vector also goes to the negative. So we're just adding the two up. So the electric field can be written as eta over 2 epsilon naught plus eta over 2 epsilon naught. So the electric field between the plates is given by eta over epsilon naught, where eta is our charge density, of course. So this is the electric field between the plates. It's given by eta over 2 epsilon naught. Sorry, eta over epsilon naught. So if eta is equal to charge per unit area, then we have the electric field between the plates of a parallel plate capacitor, which is charged to a total charge Q, will be given by Q over epsilon naught A. Like that. Any questions at this point?
What is that over epsilon naught?
Q over epsilon naught A.
Oh no, the one above it.
It's eta. That's the charge density eta.
Oh. Eta?
Eta. ETA. The Greek letter eta. So if we draw the parallel plate capacitor again, this is what we have. So we have the positive plate, the negative plate, the electric field between them is that electric field that I've just shown you. So if this is a positive charge Q, negative charge Q, then this is the electric field E, and E is equal to Q over epsilon naught A, where A is the area. A. A is the area of one plate. Okay, so A is the area of the plate. So at the edges here, you're going to have fields that go out something like that. But if we have the capacitor large enough, we won't have to worry about the fringe fields. We will just have a very uniform field in the middle. So as I've mentioned, the parallel plate capacitor allows us to have a uniform electric field. So you can see the lines that are in the middle are straight. So that means the electric field is uniform in between the plates of the capacitor. And it's also a constant, as you can see.